Okay, a couple mathematical modeling problems using integration where we have word problems. So on this first one, we have a robot that's been programmed so when it starts to move, its velocity after t seconds is given by this function, 3t squared, feet per second. All right, so they've given us a function modeling velocity, and we want to answer the questions, how far will the robot travel during its first 4 seconds of movement? So this change is going to be modeled by the integral from 0 to 4 seconds with our function, our velocity, 3t squared in here, dt. So this is the answer in part A. To accomplish this, what we want to do is integrate what's on the inside, the integrand. So we'll bring the 3 along, we'll increase the exponent by 1, so the 2 becomes a 3, and then we'll divide by that new exponent. And this will be evaluated between 0 and 4. Now this is kind of nice that the 3 over 3 is going to make a 1 out in front, so really our function is just t cubed evaluated between 0 and 4. Our bounds of integration. So to do this, we'll plug in the 4, replace the t with that, and subtract away when we plug in the 0 and replace the t with that. This works out pretty nicely that it's going to be 4 cubed minus 0, so 4 cubed is 64, and our units on this are going to be in feet. Okay, for part B, not too bad. How far will the robot travel during the next 4 seconds? Okay, so the next 4 seconds are going to be our times have just changed for our end values. So it's going to be from 4 to 8 would be the next 4 seconds. Still the same velocity function. The integrating is going to be very, very similar, right? You bring the constant, the 3 along, increase the exponent by 1, divide by the new exponent. It's just that the bounds of integration have changed here. So as we evaluate this at the bounds, we're going to go 8 cubed minus 4 cubed. Now bigger numbers here, but it's going to be 512 minus 64, which is going to work out to be 448 feet would be our units. All right, the next one, what we want to do is suppose that t minutes after putting 1,000 bacteria in a petri dish, or in a petri plate, the rate of growth of this population is going to be 6t bacteria per minute. So it's illustrated over there on the right hand side with the graph. It's a linear function, the 6t, so that's up 6 and to the right 1 for each one of those. So it's the red line over on the right hand side. But we want to answer a couple of questions about this. So on the first one, how many new bacteria are added to the population during the first 7 minutes? So on part A, we're trying to find out in the first 7 minutes, how far did this change? So that's going from minute 0 to minute 7. Our function that modeled the rate of change was 6t, and we're going to include a dt at the end here because t is our variable. All right, to integrate, I'm going to bring the 6 along, increase the exponent from a 1 to a 2, divide by that new exponent, and then this is still evaluated between 0 and 7, so those bounds go at the end. This will reduce to 3t squared, evaluated from 0 to 7. At this point, we want to fill in the upper bound, the 7 first, goes in for t, and then fill in the lower bound, the 0, for the t, and subtract that away. All right, this shouldn't be too bad. What we're going to get is 3 times 49 minus 3 times 0 is going to work out to be 3 times 49, which would be 147. The label there would be 147 new bacteria. In part B, we want to know what is the total population going to be after 7 minutes. So what we want to do is start with our beginning population. The 1,000 was the starting population. And then we want to add the amount of change. And we already illustrated that amount of change with that integral in part A. So we found that it was going to increase by 147 bacteria over the first 7 minutes. So our total is going to be given by 1,147 bacteria. All right, so I hope this helps out as we're trying to model word problems using integrals, definite integrals on these. They're not too bad. Use that power rule, and you should be able to get through these. Good luck.